Okay, this is the review for GIS 205 for test number 2, exam number 2, whatever you want to call it. It's going to be a little bit fast because this is really a lot of basic information that you should already know. So we're going to cover it, and hopefully this will help you not have problems with the exam. First off, SQL, Structured Query Language. You need to know what it is and be able to explain that it's a programming language that you can use to query things. When you go to build these expressions, that consist of Boolean expressions and connectors, things like ands and ors, or nots, and that kind of stuff. This is just an example of how the different types of operations. There are 3 types of operations that can be performed. Subsets, and on subsets, that means you can either select from that, add to it, subtract to it, or select another subset. Relational database query works on a relational database. It's a query of a table. Not only selects a data set in the table, but also selects all the related data in the subsequent other tables. Spatial data query refers to spatial data, and when you retrieve it from a subset, working directly with the features. So you can select a feature with a tool, and then that'll select the spatial data, or you select the spatial data and it selects the tool. Or it selects the feature, I'm sorry. So what are some of the expressions that we use? Contain, completely contain, clementine contain, intersect 3D, or cross by, proximity, adjacency, those sort of things. Let me redo this one. Vector data analysis uses spatial features, points, lines, polygons. Accuracy is better, but it depends on what you're looking at. Topology can also be a factor for some vector data analysis, such as buffering and overlay. If the topology is not set up, it can create problems. Buffering, based on the concept of proximity, buffering creates 2 areas, one within a specified distance and one outside that. The area within is called the buffer zone. Buffering around points creates circles. Around lines create elongated segments. There's different variations. You can buffer distances according to the values of a given field. You can buffer around features. You can buffer like intrinsic rows, or you can create a distance thing to indicate where buffers are. Dissolve, not dissolve with buffers. If you don't dissolve, you get buffers like you see at the top. If you dissolve your buffers, you get the buffers at the bottom. Overlay is a common feature that we use. You take 2 different geometries, you place one over top of the other one, and it intersects and creates all possible combinations of features so that you don't lose any attributes when you combine them by creating a one-to-one cardinality. Example. So we're going to look at some of the different types: point and line, line and polygon, polygon, polygon. Pretty straightforward what happens with the polygons. Overlay methods based on Boolean connectors, ands, ors, and not ors. An overlay operation called intersect uses the and. Union uses the or, and not or is a symmetrical difference or difference function. That's what union looks like. Keeps everything. That's what intersect looks like. Only keeps the things that are common to both. The symmetric difference, or the not or, does that. Identify method produces an output that has the same extent as the input, but the output includes any of the stuff that would be identified by the other layer. Slivers, tiny little pieces of things that are created because of bad topology or differences in how things are digitized. It's basically tiny little parts of polygons or lines that occur because of the processing that can create problems. You can control this using snapping tolerance, cluster tolerances, that kind of stuff. These are what we're talking about. Combine these lines. Lines don't quite line up. You get all these little tiny little bits. Those are called slivers. Cluster tolerances help eliminate that. Error propagation and overlay results in inaccuracies. So you do one overlay and another and another and another. Each time you do it, you create little tiny things like the slivers, which then propagate to create more and more and more. And so you need to control these things from the outset, because otherwise each step in a series of overlays contributes to additional error being generated. Pattern analysis studies the spatial arrangement of points in 2 dimensions. Random, dispersed, and clustered. Generally, that's what points or data looks like. Patterns can either be local or global, highs or lows. There's lots of different techniques, Moran's eye, the G statistics, etc. Point pattern analysis. Nearest neighbor uses distances between each point to determine if a point pattern is random or regular or clustered. Ripley's K looks at dispersion over a range of distances. Spatial autocorrelation is what we count on in GIS because it's the basis of predicting things in between known points and interpolation in general. Spatial autocorrelation measures the relationship among values of a variable according to the spatial arrangement of the values. The relationship is described as highly correlated if the values are spatially close to each other, and independent or random if no pattern can be discerned from the arranged values. Clustering, the G statistic helps you identify clusters, in other words, high spots, and clusters of low values, cold spots. It's where there's high values surrounded by high values or low values surrounded by low values. Feature manipulation. GIS has a lot of stuff that you can use to do this. This would be things like dissolve, clip, append, select, eliminate, update, erase, and split. These are all ways that you change features to give them a different or a new geometry. This is an example of dissolving boundaries. You got ones that touch together and threes that touch together. When you dissolve the boundaries, you get a new polygon that is the combined 1 and the combined 3. But you notice there's a 1 in the bottom. It's because the ones don't have to be contiguous. They can be disjointed. What the clip layer does and what the output looks like. Append. Append, it brings things together. It adds the data to the other data. The key thing to remember is that it does not care whether the data already is there, and so you can end up with duplicates. Eliminate removes some of the small slivers around a boundary. One way you can do that. Update replaces the input layer with the update layer and its features. The dash lines are for illustration only. They're not part of the update layer. So you got this little update you added in, and then it just erase. Again, the circle is the erase part, and it takes that out of the other. Input layer, split layer, you get new outputs divided up by those. Raster data is based on cells and rasters. You can have, it can be formed at a level of individual cells, groups of cells, or cells within a raster. Some use a single raster, others use multiples, and so there's different ways you can do that. Remember that raster data analysis is related to the type of data, so there's certain things you can only do because of the types of data. In other words, if it's numeric, you can do some things. If it's categorical, you can only do others. Neighborhood operations involve a focal cell. Sorry about that, my phone was ringing. Anyway, neighborhood operations involve focal cells instead of cells in the surrounding cells. You can set it up in a lot of different ways, and you can measure any number of different statistics. So you can select neighborhoods like rectangles, circles, annuluses, or wedges, and we can talk about some of those later. There are the shapes, and you can see the target area would be the X, and the neighborhood would be the grayed in boxes, and you can see how that works. And then it recalculates for each cell. For example, in box A, you take the middle cell, that's your target, and so your neighborhood is the gray area, and so if you average all those together, that center cell, that is it's a value of 1 in A, will be a value of 2.11 in B. Same concept here. And zonal operations work for a group of cells with the same values or like features. They're called zones. Zones may be contiguous or non-contiguous. A zonal operation can work with a single or multiple rasters. It measures any number of things like the geometry or the area or whatever. If you have 2 rasters in a zonal operation, one input raster and one zonal raster. The zone produces a zonal operation produces an output raster which summarizes cell values in the input for the zones identified in the second one. And this just shows how thickness and centroid, two large areas, and this centroid's right in the middle. Zonal, we'll talk a little bit about more zonal stuff. Physical distance measure operations. Physical distance can be straight line, which is Euclidean distance, or they can be calculated straight lines from cells at the source. So you go from the middle of one cell to the middle of another cell, and you can get that distance. You can also measure distance continuously. In this example, you have a stream network, and we measure how far every cell on this grid is from the feature itself from the stream. Allocation and direction produces a raster in which cell values correspond to the closest source. That's kind of what we're talking about. Direction produces a similar thing, but instead of how far is it to a particular source or a particular feature, it's what is the direction, in which direction am I closest to the nearest feature or structure. This slide sort of explains some of that. You can read that there at your discretion if you have questions. Other operations would include things like clip and mosaic, raster data extraction. You can do a lot of different things with that, as well as aggregate and do regional. Analysis mask is the sort of fundamental kind of clip concept, but for rasters. So you have a data layer A, you have a feature B that is a mask. You apply the mask to the raster, you get a new raster that only includes the area that was in the mask. Hence, the analysis is limited to the mask, or effectively you can also do this as extraction by mask. Same concept. Map algebra. It's an informal language of syntax similar to algebra that can be used to facilitate the manipulation and analysis of raster data. In other words, you take a raster and then you apply some math function to it to change it, or use a math function between multiple rasters if you like. Vector versus raster-based analysis. Vector analysis and raster analysis represent two basic types of analysis. They're treated separately because GIS can't run them together in the same operations. Generally, you have to choose one or the other based on the analysis and the data that you have. Terrain mapping analysis is pretty much mostly raster-based, but not entirely type of operation. We use things like contouring, which can be vector, hill shading, hyposymmetric tinting, 3D perspective view. A lot of these are actually raster. Terrain analysis includes quantitative measures of the land surface, such as slope, aspect, and surface curvature. Geomorphometry is a science of topographic quantification. Slope, aspect, and curvature among the land surface parameters that are studied often in geomorphometry. Data for terrain analysis and mapping. The first thing it starts with is a DEM. Sometimes we can use a TIN, but mostly DEMs. A DEM represents a regular array of elevation. It can be converted to an elevation raster by placing elevation points at the center of the cells. And do this a lot of times. This data is collected from aerial photographs, but sometimes it's also collected from LiDAR. TIN approximates the land surface by using a series of non-overlapping triangles, hence the triangulated irregular network, because they're not uniform in shape. TIN approximates the land surface with a series of non-overlapping triangles. Like I said, DEM is usually primary source of compiling TINs through an algorithm that works off of the individual elevation measures. But a lot of DEMs are in fact rasters. Input data in the TIN. You can use a lot of stuff, GPS coordinate data that you can have in tabular form, or just raw LiDAR data. You add break lines in a TIN where you want an elevation change or feature to be identified, and then it redevelops the triangles so that the terrain can more evenly match those areas. Terrain mapping includes contouring, vertical profiling, hill shading, and all those other things we talked about earlier. This is a contour line map. This shows how it works. You got a line at 900 feet, so wherever your points are, from one elevation to the other, from 850 to 950, it finds the center point, which would be in this case 900, and the next line goes from 850 to 1000. It figures out where 900 should be there, etc., connecting the dots. Hill shading. You position the sun at a certain angle, give it a certain direction, a certain altitude, and it indicates where the shadows would actually be seen on the landscape. Hypsometric map shows differences in elevations, very similar to contour lines, but its color is the big addition here. 3D perspective. How 3D viewing works, you identify these parameters, where you're looking from, how you're looking at the angles and such, and then it calculates out what it should look like. You can take other data and drape it over a 3D image and give you a pseudo 3D surface of whatever the feature was. And this was just a really bad 3D perspective view of an elevation map. Where this concept is really interesting is when you start extruding buildings and structures relative to the 3D model. Slope and aspect. The slope is the first derivation of elevation and is measured by the rate of change of elevation and surface location. It can be in percent or in degrees. Same with aspect. It's the directional measure of slope. In other words, it is the direction of the steepest slope from a particular spot. Generally measured in degrees, but it can often be represented in terms of north, south, east, west type directions. Basic idea of slope being rise over run. And this shows how the northeast, southwest can be divided up into north, northeast, east, southeast, south, southwest. And then angularly starting at a particular location, you go a certain number of degrees, and depending on which slice of the pie you fall in, you could say that the aspect is, for example, east. And this is how you convert between the two. Various algorithms for computing these things. Slope and aspect are real measurements, and they tend to be directed perpendicular to the unit. Different approximations are out there, different ways you do it. Usually it's based off of an elevation raster and a 3x3 moving window, but that is not always the case. You can have situations where you measure slope over a larger area and not just a small 3x3 moving cell. So this shows how you can measure what aspect and slope are relative to a particular landscape. And this is Ritter's algorithm for computing it. I'm not going to ask anything about this or about horns. Computing algorithms for slope and tens, again, I'm not going to ask you about those too much. What are some of the factors that affect it? This is something that you need to know. It's the slope, an aspect that can be influenced by the elevation, the resolution of the DEM, the quality of the DEM, the algorithm that you compute it, and then any local topography effects can also complicate it. 3 different landscapes produced from 3 different resolution DEMs, a 30 meter, a 10 meter, and a 1.83 meter. And you can kind of see very plainly here by how plain the picture is how much or little detail you get relative to that resolution. Same way with slope. Surface curvature, it's the next step from this. It's not just looking at whether or not how steep or downhill or uphill something is and what direction it's facing. It's looking at the configuration of that slope itself. Is it convex or concave? Up and down, is it convex and concave across? And this comes back to the ideas of profile curvature and plane curvature. Rasters and TIN as inputs for terrain mapping analysis. Rasters and TIN differ in data flexibility and computational efficiency. The main advantage of a TIN is that it is flexible with input data sources, but the computational efficiency is the main advantage of using rasters. In other words, you can do so much more, so much faster with a raster than what you can with a TIN. Remember the old saying, vector is corrector, raster is faster. Viewshed analysis, it's like a watershed but with your eyes. It identifies the areas that you can see from a particular point of view. Here would be an example. You have a point up there on the hill that is identified as your viewpoint. From there, using the terrain model and a line of sight calculation, it identifies what parts are visible and what parts are not. Line of sight is a basic operation. It connects where you're at to everything else and looks for things that block it. If something can't be seen from another area because in that direct line of sight path there is land or space blocking that view, then that area is not identified. This is just more examples of how that would work, what that would look like. View sheds can be derived from elevations or tins. The tin-based view shed can classify an entire triangle as either visible or invisible, or classify the visibility of 1, 2, or all 3 points of the triangle, whereas rasters can identify it on a cell-by-cell basis. The cumulative view shed is the output of the view shed analysis. It's a binary map. It's a 1 or a 0, visible or not visible. And it would look like this. So what's the accuracy? Generally not very good. They tend to be pretty rough. What are the parameters that influence it? The height of the observer, the viewing angle, the viewing radius, the vertical viewing angle, the limits of the Earth's curvature, and the height of the trees could all contribute to blocking or not blocking particular view sheds. Got 2 maps here. One uses visible areas with an infinite search radius, and the other one uses 8,000 meters, meaning that it doesn't expect you to be able to see any further than that under any circumstances, and so it just simply doesn't identify those areas that they think is beyond that. Watershed analysis refers to an area that's drained by a particular set of topographic divides. In other words, if you imagine a drop of water falling from the sky and hitting the Earth's surface, but instead of soaking into the ground, it simply rolls across it downhill. It is the areas in which feed particular streams and rivers, and we can calculate these from the This shows how watersheds are delineated and superimposed on a 3D landscape. So when you do this, there's different spatial scales. It depends on what you want to look at. Is it a small watershed or a large watershed? How much area comes into it? How many streams join up? There's lots of different ways to do it. You can use something called a point-based method, where you pick an area and you identify the watershed that's uphill from there. There's multiple steps that go in it. You start out with elevation data. From that, you calculate flow direction. In other words, from an individual cell, what's the steepest downhill slope? Well, there's different ways of calculating, but that's the most simple. Once you know the direction, you can then calculate the number of cells that accumulate into other cells, and then that's the first step in doing a lot of calculations. Flow accumulation raster calculates for each cell the number of cells that flow into it. Darker symbols meaning higher, and this is an example of flow accumulation raster, and you can see that as the number of cells increase, you begin to form a stream network. Stream networks, the derivation of stream network is based on the channel initiation threshold. In other words, you say when X number of cells drain to a point, that point no longer becomes just an area where things are draining to, it actually becomes a stream. This just illustrates that a little. In terms of talking about streams, we have outlets, reaches, and junctions. Junctions where 2 streams come together. A reach is a section of a stream, and an outlet is at the end of the watershed. And this is an example of an area-wide watershed, and you can see how within it there are so many sub-watersheds and streams. Point-based watersheds have one watershed associated with each point, and typically these points or gauging stations are placed on streams so that they can monitor the height of the stream or the quality of the water. The analysis that's most similar to this in GIS is something called pour-point analysis. That's where you basically identify that point, and then it identifies everything that drains to it. Here's an example of what pour-point-based watershed areas look like. You can also snap by pour-point. A pour-point is not located directly over a stream. You can use your snapping tolerances so that it pulls in, so that it lines up with the stream network, so you actually get the part of the watershed you're looking for. Like this. And here. There's lots of algorithms for deriving this kind of stuff, and I'm not going to get questions about that. Pour-point, black circle, again, that's about all you need to remember. So what influences watershed analysis? That would be things like your DEM resolution, the flow direction, and the flow accumulation thresholds that you set will greatly influence exactly how this stuff all comes out. Again, resolution, stream network, segments, flow accumulation, stream network, based on different cell counts and how that impacts it. Same stuff. Data display and cartography. You want to make a map, you want to make a good one, certain things you need to do, and you need to do them well. Common map elements are things like the title of the body, the legend, the north arrow of the scale, the acknowledgments, the neat lines, the map borders. Other things can be graticals or grids, the name of the map, the projection, an inset or location map, and any data quality information. This is the kind of thing that I would particularly give, might ask you to name a few of these on the exam. This shows what the map elements are and what they look like. Cartographic representation is cartography is the making and study of maps and all their aspects. Cartographers classify maps into general reference, thematic, and qualitative or quantitative maps. Spatial features and map symbols. To display a spatial feature on a map, we use symbols that indicate what things are, where they are. There's certain rules that we have related to this, and we can also change these things relative to certain variables by changing colors and sizes and shapes and such. So here's an example where we have streams that are black, we have watersheds that are shades of gray. We can change and represent things different ways cartographically by, for example, using different color shades, different size boxes. We can use the same color but use different variations of it. We can use textures, we can use shapes, we can use patterns. The problem with color is that sometimes people are colorblind, and that sometimes we design things in color and they're displayed or printed in black and white. And so you need to make sure that you design your map for the intended audience, for the intended target, for the intended media, and the way it's going to be displayed. Make sure that you use color schemes that are representative of all that. If you know it's going to be printed or used in black and white, you probably want to design the map in black and white, because if you design it in color, it's not going to look very good in black and white. The other thing we do with our data is classify it. There's multiple techniques: equal interval, geometric interval, equal frequency, mean, standard deviation, natural breaks, and user defined are all different techniques for how you can classify your data. Here are a couple examples. The Jenks natural breaks method is the default in ArcGIS. Remember that it identifies the natural clusters in the data by creating the number of groups that you tell it to create, and it sizes the groups up such that the average standard deviation across all the groups is as small as possible. And let's see here, generalization. You can't make real world representations perfectly in any GIS. That's just too much requirement for storage and space and whatnot. So we make generalizations. In other words, we sort of scale things out to be crude representations, and depending on the scale we're looking at, they might be even more crude. Types of maps: dot map, choropleth, graduated, simple, pie chart, flow map, isotherms. These are 6 really common quantitative maps. In other words, they actual measure the quantities of the types of things. Rasters are cell-based maps, and they can be categorical or numeric. In other words, qualitative or quantitative. This is elevation. This would be quantitative. Map design is a visual plan to achieve a goal. It's all about how you lay out your map, what you want to do. You need to have some elements of layout and visual hierarchy. It's what you need to understand, and we'll look at some of those here in a second. Attribute data is stored in tables, rows and columns. Each one represents something unique. You can only store one piece of data in a raster model, whereas vector data allows you to store all kinds of stuff. So here is an object-oriented based attributes for a shapefile, for a shape field. So it has the shape area and shape length. If it was a value attribute table, it lists the attributes and values and counts. There are 2 types of attribute tables in vector data. For attribute table and non-spatial attribute. Feature attribute tables must have the spatial data. Every vector data set must have a feature attribute table. For georelational models, the feature attribute table uses a feature ID to link to the feature's geometry because it's stored separately. Non-spatial attribute table does not have direct access to the feature geometry, and non-spatial data may exist as any number of other files that can be linked to it. A database management system is a software that enables us to manipulate a database. Types of attributes, the things that we look at, numbers, text, characters, dates, binary, large objects, etc. Database design, there are 4 types: flat, hierarchical, network, and relational. Relational databases are the standard in GIS. This is an example of what they sort of look like. So a flat file is just everything in one single file. Hierarchical is where data is sorted into groups and the clusters and types and whatnot, so that things are easily identifiable. Networks is a one-to-many kind of setup, and relational things are things that are related to one another. So a relational database is a collection of tables connected to each other by keys, primary keys. One or more attribute values that uniquely identify a record. Normalization is something that we have to do with our data if we want to make use out of it in many cases, because we have to standardize variables so that things don't overwhelm models and whatnot, and they're on the same scale or the same value, and the way we do that is by normalization. We also use it when we're dealing with modifiable area unit problem as well. Types of relationships that may contain, we're really talking about cardinalities. In other words, one-to-one, one-to-many, many-to-one, many-to-many. Here are the examples. Joins identifies things that are common to both tables and 2 data sets and brings them together. Relates is a temporary construct that when you identify things in one table, it identifies them in the other, but it keeps them physically separated, whereas a join physically brings those together. Both of these are temporary. Modeling process. Figure out what your goals are: the who, what, where, when. Define the best criteria. Bring it all together. What are the weights? You collect the data, you run the model, you validate, you have results. You do it again and again and again until you end up with a model that works. What are the keys to success? Document what you're doing, display your results, apply your model, engage and defend in what you've done. So, model problems. Spatial bias. Sometimes the data that you use might have been collected for another reason, so there could be some spatial bias into that data. In other words, the points may be selected relative to some other question, and that question could be impacting your outcome. Spatial autocorrelation is something we count on with GIS, but you need to understand the implications and you need to test for it so you can determine what, if anything, is spatially autocorrelated. Correlated layers is when you have multiple data layers that are similar or behave similar or are responding to some similar change in your spatial extent or your spatial information. In other words, you might have multiple parameters that are related to elevation, and so they all track the same thing, and then they're over-representing that phenomenon in your model, and so you need to identify these things that are multi-collinear and eliminate them. Geographic extent and resolution. Analysis dictates location, location dictates extent, extent dictates resolution. Data quality is defined as the suitability of data to answer a particular question. And so you need to be able to defend your decisions as to whether or not data is acceptable or not. Basic suitability model, finding a specific location for a specific use is at the crux of suitability modeling. You define a problem, you establish some criteria, you choose the tools that you want to use, and use some logic about this. You collect the data, you make selections, you evaluate results, and then you display or apply those results. Now, it seems pretty straightforward. It's an iterative process. You work through it multiple times. The specifics, it shouldn't matter the order that you do the various results. You want to try to make your model efficient by eliminating as much of the territory that doesn't fit the model as soon as possible in the process. You want to do some sort of sensitivity analysis to make sure that a particular variable isn't controlling your model too much. You want to evaluate your output terms, your weights, and your other variables to make sure that they're set properly. You look at the techniques. Are you going to create these various derived layers? Are you going to use base data? Are you going to use overlay functions and map algebra, raster calculations, and reclassification? Figure out what you need to do and try to incorporate it into the modeling process in an efficient way, so that it makes the process easier and faster, but also so you have the ability to spot problems. How do you rank or rate suitable locations? It's not always just 1 or 0, yes or no. Sometimes you have to rank things like, for example, 0 through 3, being not suitable, suitable, very suitable, or like perfect. And then you can do things like add weights or fuzzy functions to this. A weighted overlay assigns a value to each source layer. Fuzzy is a continuous scale from like 0 to 1. And so both of these work properly. When you create suitable layers, before you combine, they must be standardized. And so you have to standardize. If you rank things, you're sort of standardizing them. And if you weigh things, you're sort of standardizing. And if you multiply standardizations, you're in somewhat of a weighting thing. So there's different ways of doing it, but you tend to want to stick to a single scale. You want to use, whether it's 1 to 3 or 0 to 4, 1 to 7, etc. You need to stick with it. There should be 3 to 9 categories in those scales. Exclusions are very helpful because you can kick out stuff that you don't want from the get-go. Don't be afraid to add a 1 or a 0 Boolean layer in there to eliminate locations to reduce the amount of stuff you have to process. You can use models to create a virtual what-if scenario. It allows you to examine multiple locations or competing scenarios, or change your variables and see how it affects the outputs. You can also do the exact same thing with the various other ways that you can do the weights and the ways you can combine your layers. You could literally talk for a day about just how you could create different weights and how you can combine the different layers. So we're not going to go too much further in detail about that today. More on the fuzzy overlays are pretty much basic logic theory, sometimes called fuzzy logic. So imagine a scale between 1 to 10. 1 is misting rain, 10 is a 500-year flood. The fuzzy logic is simply a numerical or a mathematical function that you generate that places things appropriately on that scale between the least and the most. You can do it for observed values where you set things as 1s and 0s, 1 being perfect, 0 being not, and everything being in between. You can use it for categorical stuff. So if you have multiple things that would work, they can get certain values. Things that are similar to that, you can give a different value. Stuff that's really not close to that could get a lower value, and things that are inappropriate could get an even lower score. And so it doesn't always have to be a perfect single gradation. It can be some degree of user input there as well. Continuous data, don't try to come up with a classification scheme for that. You tend to want to use a calculation for that because of the data volume. It'll work better. Network paths, things like infrastructure, transportation flow, time, and connectivity. Process is very similar to other GIS. You have problems, you have parameters. You create a network layer that's full of edges and junctions that represent physical infrastructure like roads and such. You have cost layers of things like elevation. You combine all this to solve your problem. Overland travel is calculated by the distance over the terrain, not as the crow flies. You can change cost to reflect weights of your pack. You can map fastest loaded versus unloaded. Or you can map shortest. There's lots of things you can do with this sort of stuff. So what is the cost surfaces? These typically on an overland map would be something like land cover. It could also be slope. But for other things, it could be other meaningful stuff like the number of stoplights, the number of lanes in the road, posted speed limits, etc.